this video, we're going to work through a principal agent problem. I encourage you to look at the link in the video description and download this handout so that you can follow along and do the mathematics and look at the graphs and take notes as we go. In today's principal agent problem, we are going to be focusing on the idea that a principal is hiring an agent to do a job. In general, a principal agent problem is anytime a principal contracts an agent to do something. It could be that the principal is an insurance company, the agent is a customer. However, you can also flip that around and say that the customer is the principal who's hiring the insurance company to perform something, to provide insurance. Any contract in general can be analyzed using principal agent problems, but the problem in a principal agent problem that we're focusing on can be one of two things: hidden actions or hidden information. Now, if it's a problem of hidden action, where the problem is that the principal can't see something that the agent is doing, we generally call that a problem of moral hazard. So hidden action, moral hazard. For example, I might hire someone and I might be worried that because I can't watch everything that they're doing, they might steal from me or they might not work as hard as I expect them to. So I can't observe whether they're stealing, I can't observe whether they're being lazy or whether they're working hard, and so this is a moral hazard problem. The other kind of problem might be where there's hidden information, and generally we will call a situation where we have hidden information an adverse selection kind of problem. Adverse just means bad. Selection means we're getting the wrong type. And the one example of a problem of adverse selection when we're hiring somebody might be that when I advertise to try to hire someone to do a job, I might not be able to tell whether this person has the right qualifications. So there's some information about this person that is hidden. So we might not be able to tell if this person has the right skills or abilities or intelligence in order to do the job that I need them to do. So that's something that only the agent, the person I'm trying to hire, would know. So in this problem, we're going to consider a moral hazard problem, and the story is going to be the following. We're trying to hire someone to do a job for us. Perhaps we need them to go mine some gold. So we have some land, we know there's some gold there, we don't know how much, and the output, the amount of gold that this person is going to dig up, is going to depend on two things. First, it's going to depend on the agent's effort level. How hard do they work? Secondly, it's also going to involve random chance, because I don't know how much gold there is in this land. It might be that on this land, when the agent goes there, there are just big lumps of gold sitting on the ground, and all the agent has to do is pick them up. Or it could be the case that the land has gold, but it's very deep, and this agent is going to have to work very hard to try to find the gold. And if they work very hard, they might find a lot of gold, they might find a little gold. So part of this is due to random chance. So we are the principal, we're hiring this agent. We're going to pay this agent wages, we're going to call that W. The agent's effort, we're going to assume, can either be high or low. So we're just restricting it to be either high or low. And we're going to call high an effort of 1 and low an effort of 0. The principal has a utility function and the agent has a utility function. The principal's utility function is simply the output level, how much gold they get, minus the wages that they have to pay this agent. Now, from the structure of this utility function for the principal, we can see that the principal is risk neutral. And this basically follows from the fact that their marginal utility of income is linear. So they are risk neutral. However, the agent, they have a utility function that is the square root of the wages minus C. And C is this effort. So it's going to cost this agent either 1 or 0 in order to expend effort. So if they're lazy, they're not expending any effort at all. And if they are working hard, it's going to cost them 1 off of their utility. So the square root of however much money they have minus 1 if they work hard, minus 0 if they don't work hard. Now the agent's utility function here is risk averse, and this follows from the fact that this agent's utility function is concave. Now I'm going to put a link in the description below to my introductory video on risk aversion and how to understand risk aversion if you need to review that. Now, a general principle: when the principal is risk neutral and the agent is risk averse, the agent is going to have to be compensated extra anytime their wages are uncertain. So you're going to have to pay the agent more if there's some risk that they're not going to get paid a constant amount, and that will play into the solution when we do that. So one other thing that we have to remember here in this kind of problem, usually the agent has a reservation utility, and in this case the agent has a reservation utility of 10. So we're going to call that UA, utility of the agent, with a lower bar on it. And what that's telling us is this agent doesn't have to contract with this principal if the principal isn't going to pay this agent at least enough money so that they can get a utility of 10 or an expected utility of 10, then this agent's going to walk away. They have some other job they could do. The output here is going to take two different values to keep it simple, and those two different values are going to be partially random and partially be related to the agent's effort. So the two values that our output can take are 400 with probability p and 100 with probability 1 minus p, assuming that p and 1 minus p add up to 1, or 100% of the probability. Now, if the agent works hard, and when they work hard, that's going to mean that it's going to cost them 1 from that C in their utility function. It's going to cost them 1 util. Then the probability that we get the high output is 2/3. And the high output is going to be 400 units of gold, or if the agent provides low effort, it's not going to cost the agent anything in their utility function from that C parameter of them working really hard. If they don't work hard, the probability we get that high payout of 400 units of gold is only 1/3. So that would mean 2/3 probability that we get the 100 when they give low effort, and a 1/3 probability that we get the low payout when they provide high effort. So that's the setup of the problem. That's everything we need to know here. So let's discuss in general how we can solve these kinds of problems. What we're talking about here is a field of game theory and economics called mechanism design. And in mechanism design, we want to design the best contract that induces the desired effort level. So what kind of effort level do we want from this agent? Do we want them to work hard or not? It depends on the payoffs, and it depends on the costs involved. So we're going to have to answer that question. What kind of effort level do we want from the agent? And this contract we want to select in order to maximize profits. Now, when we do this, there are going to be three kinds of equations that we're going to want to think about. First is a profit function. Basically, thinking about this, what is the profit function or the utility function of this principle going to be? What we want to do is maximize the expected value. So that's what we have here, maximize the expected value. And what we're choosing here is a wage contract. So W dot means there's some kind of wage function that we're going to be trying to construct here. And by choosing that wage function in the optimal way, what we want to do is maximize the expected value, or the long run average, of the quantity of output minus the wage that we have to pay the person. And this is just another way of writing that utility function of the principle that we had up here, just making it a little bit more mathematically explicit what we're trying to do here. So another equation that we're going to be thinking about as we solve this problem is called a participation constraint. A participation constraint takes into account the idea that the agent is not going to accept this contract. He's not a slave. He can walk away and he can do something else if he doesn't like the terms of the contract that we are offering. So the agent is going to reject the contract that we offer if it doesn't provide at least that reservation utility of 10 that we were talking about. And the third is an individual rationality constraint. The individual rationality constraint says that whatever contract we offer this agent, it's going to have to ensure that the agent provides the effort level that we want the agent to have. This individual rationality constraint makes sure that we're offering the agent enough money and the situation is just right to where if we want them to provide high effort, they are going to provide high effort. If we want them to provide low effort, likewise. Now, there are a few different ways we could attempt to solve these kinds of problems. The mathematical way to do this is called optimal control theory. When you tell me we're going to solve something according to optimal control theory, I am just going to nope my way right out of here. I'm good at math, but I'm not good at math. It's a very difficult sort of field of mathematics to get into. So you want to avoid solving these problems using optimal control theory if you possibly can. The way that economists will typically try to approach these problems is to follow the ideas that Grossman and Hart in 1983 set out in their paper, An Analysis of the Principal Agent Problem. Given this is an econometrica paper, they don't really give you step-by-step instructions very clearly. So Fudenberg and Tirole in 1990, another econometrica piece, actually did try to lay out a little more clearly what the steps are and what they call a three-step method. But here's the thing, and this is a problem that we face in economics quite a bit. Fudenberg and Tirole, in their working paper, actually set this out pretty clearly. And so you can still find that working paper. It's MIT Economics Working Paper number 494. In their working paper, they discuss what they call this three-step method in order to solve these kinds of problems. And it makes it pretty clear what you should be thinking about. But as what happens quite often, the final publication version that was published in Econometrica cuts this nice little section out. So whenever you read one of these papers in a high-end journal like Restat, Restud, or Econometrica, Rand Journal of Economics, sometimes they have to condense what they're doing into such a tightly written short way that they leave a lot of steps out, and it's not their job to explain it to you very carefully. But let's look and see what they had to say in this working paper, because I think this is very helpful. They say, to solve the principal agent model with commitment, Grossman and Hart use a three-step procedure. The first step is to characterize the set of incentive-compatible contracts that implement a given level of effort or a given distribution over levels of effort. So in other words, what they're saying is the first step is to figure out what sort of wage levels, what sort of contracts would cause the agent to provide a high effort or to provide a low effort. So once we figure out what those wage contracts look like, that's the first step. Then they say the next step is to find which in the set of various wage contracts that would provide high effort or provide low effort, which element in those sets of contracts would give the desired level of effort at the least cost to the principal. In other words, what's the cheapest way to get this person to provide high effort? What's the cheapest way to get them to provide low effort? There are probably a lot of different wage contracts that would do this. Find the one that is cheapest for the principal to actually implement. They go on to say here that one expects that this least cost contract will give the agent 0 ex ante rent. In other words, the agent's individual rationality constraint will bind. What they're saying here is we expect that this cheapest contract, cheapest way to get the person to provide high effort or low effort, is going to provide this agent with exactly their reservation utility. Or you could say their reservation utility plus a tiny bit, plus epsilon. So what this means in this context is since the reservation utility of our agent is 10, we expect that the contract that this principal picks is going to be one that provides the agent their reservation utility, or maybe a tiny bit more, and we might call that tiny bit more epsilon, just some infinitesimal amount. And we'll address that whenever we get into finding the solution. Finally, last step here, choose the distribution over effort that maximizes the difference between the principal's expected revenue and the cost of the agent's compensation. In other words, once we figure out the cheapest contract to get us high effort from the agent and the cheapest contract that would get us low effort from the agent, let's ask the question, okay, now that I know how much it will cost to get high effort, and I know how much it will cost me to get low effort out of the agent, which of those two effort levels and costs actually provides me with the highest profit level? And then you can go back and pick the best contract for the effort level, and we've solved the problem. Okay, now let's solve the easiest version of this problem. And the easiest version of this problem is going to assume that the principal can actually observe how hard the agent works. So there is really no moral hazard problem here because there's going to be no hidden action. So let's solve this problem assuming that everything is observable, and that will help us understand the more complicated problem of solving this problem when effort is not observable. So I wrote all of our information that we need to keep in mind up here at the top. So we have the principal's utility function, output minus W. We have the agent's utility function, the square root of their wages minus the cost of effort, which is either 0 if they're lazy or 1 if they work hard. The reservation utility of the agent is 10, so they're never going to accept a contract that gives them a utility level or an expected utility level less than 10. The output, 400 with probability P, 100 the rest of the time, and if the agent gives us high effort, the probability of the high output is 2/3, low effort, the probability of that high output is only 1/3. Just refresher formulas here, the expected value when an outcome is random is just the sum of the probabilities times the outcome, and expected utility is the sum of the probabilities times the utility that the agent would get in this case if there is a random outcome in terms of their wage. There's not going to be in this case because the principal is going to be able to observe their work effort and reward them based on how hard they work. There's no uncertainty there, so there's not going to be any uncertainty in the wages. But there will be uncertainty in the amount of output because that's random no matter what. So what we're going to do here when effort is observable is derive what we call the first best contract. The first best contract means if there wasn't any uncertainty to get in the way and cause inefficiencies, what should we do? So how would we get low effort? Suppose we wanted low effort, and we don't know whether we want low effort or high effort until we know how much it's going to cost us to get high effort or low effort as the principal. So what we need to do here is say, well, if we wanted low effort, here's the utility function of the agent. It's the square root of the wage minus C. Now, if we're getting low effort, then that C is just going to be 0, right? So we don't need to worry about that part. But in order to get this agent to accept this contract and provide low effort, we need to make sure that the square root of the wages is bigger than or equal to 10, right? Since there's going to be 0 effort, we don't really need to worry about that 0 part. So if I want this agent to come on board to take this job, I'm going to have to pay him a wage that gives them at least 10 utility. And so we just solve this for W, and we get that W has to be greater than or equal to 100. Simple enough. So the cheapest way is going to be to pay them a wage equal to 100, right? Because if we pay them less, they're not going to come on board. We could pay them more than 100, but that would not be profit maximizing, right? So we can think about this as being the set of contracts that would get them to come on board, wage greater than or equal to 100, this is the one that is cheapest for the principal. So that would be the contract they'll offer. Hey, I'll pay you $100, come work for me, and you'll get paid $100 no matter what. He'll come on board, he'll provide low effort. Now, in order to make sure that someone actually comes on board and takes this job, we might actually have to add them offer them $100 plus epsilon, maybe $100.01. But let's ignore that. That just makes it a little harder. So how could we get high effort out of this person? Well, very similarly, we need to look at the utility function of the agent, square root of w minus c, and we need to keep that at least 10. But here, if the agent's going to provide high effort, then that cost of providing effort is 1. So we need to just solve this to see, well, what wage could we offer in order to ensure high effort? Well, we can just add that 1 to both sides, right? And then we get the square root of the wage has to be greater than or equal to 11. The wage has to be greater than or equal to 121. So again, this would be the set of contracts, although we need to be a little clearer here. In reality, the set of contracts, since we can observe the effort, and we actually care whether the person provides high or low effort when we want the high effort, and low effort would be an option, we could say, well, here's what the contract is really going to look like. Pay them 121 if we observe high effort, right? And we could offer them 0 if we observe low effort. That would be a more complete description of the contract that would ensure that we actually get high effort out of this person. And there's no uncertainty involved because we're going to observe the person give us high effort. We're going to pay them $121. So now comes the important third question. Remember, step 1 was to derive the set of contracts that would provide a certain level of effort, then figure out the cheapest way to ensure those levels of effort. And now the last step in the 3-step method is to figure out for this principal, which one do they want? High effort or low effort? So we're going to find the expected value given these 2 contracts here. So let's divide our workspace into 2 parts. And let's assume over here, suppose we hired the person wanting them to give low effort, and they did. What would happen? Over here, high effort. What would happen? Okay, so if we hired the person to provide low effort, our utility function as the principal, remember, is this function, the amount of output minus the wage, but the output is random. Could get 400, could get 100, and if we're paying the agent to give us low effort, then the probability of the high output will be only 1/3. So let's set up that expected value problem down here. So the expected value of output minus wage, let's just focus on the expected value of the output here to start, is going to be a 1/3 chance that we get the 400, plus there's a 2/3 chance that we get the 100. So what's our expected value of output? So the expected value of the output, 1/3 times 400 is 133.33333, plus 2/3 of 100, 66.66666 running. So the expected value of the output is 200. Take that 200 in the expected value of output, subtract off the wage. We know the wage we're going to pay is $100 to get low effort, and our expected profit is 100. So that's the expected utility for the principal. Now, what if we paid this person to provide high effort? We're going to pay them $121 if they provide us high effort, and they will. The agent's not going to want to risk earning 0 if we see them providing low effort. Similarly, the expected value of our output is going to be now 2/3 chance that we get the high output, 400, plus a 1/3 chance that we get the low output, 100. So that expected value of the output is equal to 266.66666 plus 33.33333 equals $300. dollars or euros or whatever we have here. And then we're going to have to pay this person $121 when they provide that high effort. So the expected value of the utility of the principal here would be 300 minus 121 equals 179. So now we know which is the effort level we want out of this agent. Do we want to pay them to provide low effort, in which case we'd earn 100, or do we want to pay them to provide high effort, in which case we would get a profit of 179, or an expected profit of 179? Of course, we would want to go with the high effort here. So this is the solution to the problem when all of the actions are observable. We want this person to provide high effort. We're going to pay them 121, and we, the principal, should end up with a profit of 179 in the long run as we do this. In this particular case, it's uncertain, but we're risk neutral, so we're not worried about that. So this video has gotten long enough, so I'm going to end this here, and then I'm going to come back with a second part to this video where we go through the situation where we truly have unobservable effort, and we'll really solve the problem when you see moral hazard, where we can't observe the actions of the agent. Please join me for that next time.